Okay. Good morning. Welcome to this INdAM workshop on fractional differential equations, modeling, discretization, and numerical solvers. This workshop is held here in Rome, but is also streamed by Zoom and on the YouTube channel of INdAM. Moment.
How do I set this? Josh, I don't know how to set the background on this.
Okay, I would like to spend a few words in order to describe what is INdAM. INdAM is the institution which has founded this workshop, which is being very generous to give us financial support for this workshop. Maybe you don't know that INdAM was founded several years ago, in 1929. It was first the Royal National Institute of High Mathematics, but now usually it's just the National Institute of High Mathematics. The role of INdAM is essentially to support the research in mathematics in Italy, especially for young people, for young researchers, but INdAM tries to put connection between young researchers and experts in various fields of mathematics. And this is done by organizing workshops like this, summer school, and research professor, and lots of other activities. Basically, the activity of INdAM is carried out by means of 4 national research groups, which works, one on mathematical analysis, probability, the other on numerical analysis, another one in mathematical physics, and the other in algebraic and geometric structures. Well, so I'm very grateful to INdAM for the contribution to the workshop. I would like to thank in particular way the president of INdAM, Professor Giorgio Patrizio, the whole scientific committee of INdAM, which has approved our proposal for this workshop, and the staff of INdAM who has supported us in the organization of the workshop, in particular Isabella Esposito, Mario Petrucci, and Sabina. And usually I would like to thank all the organizing committees of this workshop, which is a very complicated workshop because we have to handle with the on-site activity and the online activity, in particular Angela Maria Cardone, Marco Donatelli, Fabio Rastante, which also gives us a lot of technical support for everything behind the broadcasting of the presentation. Maria Rosa Mazza and Marina Popolizzo. And usually also our technician, also our technician, Federico Massa. I'm getting crazy now. Well, what is the aim of this workshop? Basically, the main idea was to put together 2 communities working in fractional calculus. One main involved in specifically in differential equations, and in particular on numerical solvers for the differential equations, and the other one working on numerical linear algebra which is a task involved by the first group. But in particular, we want to stimulate the meeting between people belonging to these two communities, and usually to share knowledge. And in particular, we would promote the activity research in this field by young researchers. Today in the afternoon, we'll have a lot of presentations of early PhD students in order to meet them, to know them, maybe to create a network between more experts, people in this field, and the people who are approaching just now this topic. Okay, just a few technical information. As I always say, that this is not just an online conference, as unfortunately we have get used in all these years due to the pandemic situation. But this is an hybrid conference. We have almost 30 persons on this side. I would like you to show people in attending this conference. As you can see, usually we have some respect of rules, in particular concerning to stay far away one each other, to wear masks, and so other things of this kind. But I'm very happy that finally we are able to organize a first meeting, at least for us, this is the first meeting with people on site. That's why I have to fix again the webcam. So, as you can imagine, it's a quite complicated workshop, because we have to handle with these two different situations, online and on site. We will do our best. All the presentation will be by Zoom. I think that most of you are connected by Zoom. I hope that you can hear me and usually the other speakers in a clear way. Please, if you experience some issues, some troubles, write in the chat of Zoom, so our technician will try to handle this problem, or will try to communicate with us that something's not going well. But for people who are not able to connect by Zoom, the presentations will be also streamed on the YouTube channel of INdAM. You can see the link of the YouTube channel of INdAM, but maybe it is better for you to Google INdAM YouTube channel, and it is easier to get this channel than writing this very long web address. Okay, just. So, as I will tell you, it's difficult. Yeah, experience the first difficulty. Okay, as a result of this workshop, we plan to edit a special issue of this Springer INdAM series. It's a journal edited by Springer, which publishes textbooks, theses, multi-author books, and so on. So it would be fine for us to collect, or usually if you want, all your recent works in this book. So we will arrange later. We will give you information on the way to submit if you want to this special issue. I forget to tell you that if you are attending the workshop by the INdAM YouTube channel, not all the presentation will be streamed on YouTube channel because not all the authors give us consent. Obviously, I understand because what we stream on the YouTube channel will be recorded and it will be remaining there on YouTube. So not all the authors are willing to share on YouTube, and then for this reason, just few talks will be available on YouTube. But the talks that will be given also on the YouTube channel will remain there because they will be recorded. So I think there's nothing to say. Maybe with this last slide is sufficient to express our happiness here in Rome that the European Cup is finally at home, and his home is obviously in Rome. I'm very sorry, I don't know if there is someone connected from England. I hope yes. So we will see this very beautiful photo. I see here Martin, but I think Martin as an Irish people should not be very sad about, about this. Okay. So it's all, what time is it?
10.
Okay. The next talk, or the first keynote speaker is planned at 9:55. So we can wait a few minutes in order to be on time. Okay, and as maybe you know, the first speaker will be Martin Steines. So I will wait a few minutes in order to allow to people to connect for the talk for Martin. Okay. Okay, no, it's time. I thought it was early, but we are in time. So I can see here Martin in this picture here. Hi, Martin. Thank you very much, Martin, for accepting our invitation. Martin Steines is a good friend of mine, a very nice person. It is very, very nice of you to accept to give this keynote speech here. Maybe most of you already know Martin Steines. Steines is a chair professor at the Computational Science Research Center in Beijing, China. So I think it is afternoon for Martin. He has worked for a lot of years in Ireland, in Cork, and his main scientific interest has been for several years for singularly perturbed differential equations. He also wrote an important reference book in this field, but since some time ago, he moved to research activity in numerical methods for fractional differential equations. And now it is an expert in particular in the numerical treatment of partial differential equation with the time fractional data. Okay, I think we can move to the talk of Martin to be patient because this is the first talk in the Ireland
Thank you, Roberto, for the introduction. grateful to INdAM and to Professor Roberto Garappa in particular for the invitation to give this talk. I'm also very happy that Italy won the Euros. I would definitely be an Italy supporter in this. I got up this morning at 5 a.m. in order to see some of the extra time. I was glad the match continued until extra time. So I saw the extra time and I saw the penalty shootout. It was pretty interesting, even at 5:30 in the morning here. Okay, so congratulations, Italy. Well done. Grazie, Italia.
Thank you, Martin. Thank you.
Okay, so here we go. So this is the title of the talk, as you know already. Let me okay, so this is joint work with two colleagues. Junior Shen is a young lecturer in Chengdu, that's in south-central China. It's a long way from Beijing. Shanghai Zhen is a guy who's a bit older than Jingye and a lot younger than me, and he's in Jinan, which is the capital of the province just south of Beijing. It's about 2 hours from Beijing by a fast train. Okay, so here's the talk overview. It's an initial boundary value problem, which is fractional in time only. I'll talk about the numerical method, the truncation error analysis in time, which is the main part. This is the most difficult bit. That's these two sections. And then we'll talk about a pure initial value problem. And then finally come back to the original initial boundary value problem. So here's the problem we're going to talk about. Now, this particular problem has been studied in many papers with many numerical methods. So it's a time fractional problem. It's a Caputo derivative in time, and alpha is the order of the derivative, and throughout the talk, alpha is a constant somewhere between 0 and 1. As you will see later in the talk, to make some of the analysis work, I will have to keep alpha, in some sense, a kind of close to 1 or bigger than a half or something like this. And so here's the problem. It's a Caputo derivative in time. It's a standard elliptic operator in space. And so you have an initial condition and a boundary condition. If alpha was equal to 1, now it isn't, but if alpha equals 1, this would be a standard parabolic problem, which is straight. So the only thing that is strange about it is this fractional derivative here. And so here are some standard hypotheses, with nothing special. We just have some suitable domain or d equal to 1. This is just notation with a standard elliptic operator. And you don't need to worry too much about this apart from the word elliptic, because most of the talk will concentrate on how to deal with this time derivative up here. The spatial derivatives, the spatial operator won't give us any trouble. There are two conditions on this term here, depending on what norm I'm working in. C greater than or equal to 0, that's this guy. This is a condition that you would have if you want to prove bounds in the L infinity norm, the discrete L infinity norm, using maximum principles. And this other one is C minus a half give B. It's the kind of inequality that's standard when you're proving bounds in L2 norms for finite element methods. So at the end of the talk, I will need this condition, and I'm talking about the finite difference method in space. I will need the other condition, and I'm talking about the finite element method in space. So you need one or the other. And the functions A and B here are assumed to be smooth. I should say K. The functions are smooth and C. They're all smooth. So the only source of trouble in this problem is this fractional derivative. Everything else is assumed to be well behaved. The regularity of the solution will be the key issue, which by now is well known. Usually when you have nice data, which is smooth, like we do, and if it's compatible at the corners of the space-time domain, no matter how nice the data is, your typical solutions have some kind of weak singularity at the initial time t = 0. Now, if you have sufficient regularity and compatibility of the data, I'm not going to write this down exactly, then what you have is this, that for any fixed x in space, and x here now is d-dimensional, it might be one-dimensional, it might be d-dimensional. The solution near t equals 0 for fixed x is the initial condition plus some multiple of t to the alpha. Now this is well known by now, but it's kind of recently, I think people have taken it seriously. There are many papers that assume the solution is nicely behaved everywhere, including t approaches 0, and that's just not true in general. This is the typical situation. So a function like t to the alpha is continuous at t equals 0, but its derivatives blow up, and that's a significant source of trouble with fractional derivatives. The two main sources of trouble are, first of all, that the fractional derivative is non-local, and I should have said on the previous slide, I didn't define the Kepler derivative. I will define it a little bit later when we come to the numerical method. But it's non-local, and that causes difficulty in the analysis. And the second main difficulty is what we're talking about here, that you have a component in the solution which is continuous at t equals 0, but the time derivative blow up as t goes to 0. So some notation here, I just, for simplicity, use prime to denote an ordinary first order time derivative. We assume here, using Sobolev space notation, these are norms in space, that the two Sobolev norms of u of t is bounded by a fixed constant. This is for all t, and the derivatives behave like this. So hypotheses like this have been used by various authors. What I'm talking about back up here, if you have nice data, then sigma here would be equal to alpha sigma some constant. We do things a little bit more generally most of the time. Some of the time in the talk, for convenience, I will take sigma equals alpha. But in general, sigma is just a positive constant. So these are just hypotheses which, if sigma equals alpha, they agree with what's here. But if sigma isn't equal to alpha, then it becomes a bit more general. And for some data, if it's not so nice or not so compatible, then you don't quite have this, the situation isn't as good as this. It might be a little bit worse. You might have a situation like this where sigma is smaller than alpha, but I won't really talk about that. But whenever I want to get into details, quite often I will take sigma equals alpha. Okay, so this is just some hypothesis on the smoothness, which is reasonable. Typical solutions behave like this. And I will write it down again a few times in the future because it's not easy to remember. In previous work, the method has in various forms. I haven't described the method yet, but in various forms it's been around for a while. And the only paper that I know of that does significant analysis of it is a paper by the staff of the SIAM numerical analysis last year. It's basically the same method as I was discussing earlier about describing it. But the differential equation looks slightly different. There are two main forms of what people call fractional derivative initial boundary value problem. You have this kind of differential equation with this Kaputler derivative, or you have this kind, where this is a Riemann derivative, and they are nearly equivalent. Okay, you can transform the left-hand side of either one into the other, but at the cost of doing something perhaps bad to the right-hand side. And so I don't have time to discuss this here, but both the initial value problems, ours and the one in this paper, they have the same kind of singularity at t equals 0 that we have traditionally in data. That's the main point of the analysis, how to deal with this singularity. So they are very similar, but if you write out what I might call an asymptotic expansion or a decomposition of the solution, then when you come to higher order terms, higher powers of t, the two problems are not exactly the same. But the dominant term, the most troublesome term in the expansion of the solution for both our problem and Mustafa's problem is this t to the alpha. So you can think of this problem as being more or less the same as ours in terms of difficulty. Now, we had an assumption here, this inequality. He has a similar assumption, but it's a little bit stronger. He has slightly different powers of t, basically. So he assumes slightly more. I'll come back to this paper later and what it does. So let me talk now about the numerical method. We're going to start with a graded mesh in time to handle the weak singularity. This is completely standard by now. It's around a long time. I've again mentioned the thing I think maybe this is the first paper that used this. I learned it myself from Untitled Integral Equations, which are closely related to these class of problems, and these graded meshes are standard there. So let them be a positive integer. On R will be some kind of mesh grading that we can choose. Later, If R is equal to 1, we have a uniform mesh. More generally, this is the mesh. So when R is equal to 1, you can see it's uniform. If R is bigger than 1, which is probably what we would use, then the mesh points are clustered towards t equals 0. You bunch up the points near t equals 0. And the idea is to have a finer mesh near t equals 0 in order to handle this e to the alpha component. So we need near t equals 0 and to handle other components as well. That's the most troublesome. So the big issue or the big question later on will be how exactly should one choose alpha? And our theory will tell us how to choose it. This is just notation. Or n is the width of the nth dimension interval. And basically the points are near t equals 0. In other words, when n equals 1, 2, etc. And as n gets larger, tau n gets bigger and bigger. So this is the graded mesh, and I repeat, we get to choose R, and for the moment we have no idea how to do it. The theory later will tell us how to choose R. Okay. So let's come to the definition of the Caputo derivative. So the Caputo derivative of all the alpha and beta 1, and this is another standard notation, but definition that doesn't talk about it because I didn't need to use it. So the Caputo derivative is defined as follows. For fixed x, with limited in time at the point t is, you take the time derivative of the solution of the function u, you multiply it by a certain rate, and you integrate from 0 to t. And some short notation for this, which is convenient later, is take the time derivative of u, and then apply this integral operator, which, as you may well know, is the Riemann integral operator. And it's defined like this for any positive beta. It's this, and the weighting function here in this guy is a constant times e to the power of beta minus 1. So here when I write 1 over 1 minus alpha, you will see the function a lot later. This means basically t minus s to the power of minus alpha multiplied by a constant. The constant doesn't cause us any trouble. But t minus s to the power of minus alpha, as you can see, blows up as s goes to 2. And so this is a weak singularity. There is a singularity between this ternary and this weighting function that multiplies the derivative. And that certainly causes difficulty. That's the definition of the Caputo derivative. Now there's a very standard discretization of it, the L1 discretization, very well known. It appears in many, many papers. And the way it's defined is you take the definition of the Caputo derivative, and on your mesh, for us, our graded mesh, you replace u by a piecewise linear interpolate of u, or now switch notation for any function v. You replace in the definition of the Caputo derivative of v, you replace v by the piecewise linear interpolate on the graded mesh. So you interpolate in time, you do nothing in space. And then the L1 discretization is defined to be, well, this is the definition of the Caputo derivative, same as up here, and you simply replace v by this piecewise linear v. The derivative is defined almost everywhere, piecewise linear, and so this expression is well defined. And this is the L1 discretization. As I say, it's in many, many papers. It's very thoroughly studied by various people. Okay, that's the L1 discretization. The method that I want to use is sort of, how to describe it, a fancier, jazzed up version of this L1 discretization. So we're going to work with something called the average L1 discretization, and I'll write it as L1 bar to indicate an average. Here's the definition. The L1 discretization of the Caputo derivative is this. This is the same as the slide. This is defined at every point, not just at the mesh points. In the L1 bar discretization, we use this notation. Is defined at each mesh point to be the average, the mean, of the standard L1 discretization over the interval that leads to that mesh point. So the average L1 discretization at the point Tn, I compute this guy in here is the standard L1 discretization. It's the same as this. You compute this at each point t between tn minus 1 to tn, and then you average them. Remember, this is the length of the interval from tn minus 1 to tn. So this is the L1 bar discretization, and this basically is what this talk is all about. Some other things come in later, but this is really what we're here. So this is the definition. Obviously, it's a bit more complicated than the L1 discretization, and it's certainly more difficult to analyze, but it has a payoff. And this is the payoff. If the mesh is suitably graded, and we will find out later what does that mean, how much grading we need. Numerical experiments show that the L1 discretization has dissonant accuracy. This is well known. But the L1 bar discretization, the one we're talking about now, is better. It's 10 to the -2 accurate. So, especially if alpha is close to 1, which is often the case in models and will be the case in our theory to some extent, this is close to, if alpha is near 1, this is then first order accurate, that's all. Whereas this is second order accurate. And when I say accurate, I mean this is the order of convergence that you get in numerical experiments. So this is the situation. How do you prove this? Well, it's not easy. The L1 bar discretization, now it has various names, and I should warn you, this is our name for it. I think it's the best name because it really is an average of L1, but people have called it various things. Like in this paper here, they call it the L1 plus scheme, and I think other names have been used as well. Mustafa's paper, I don't remember what he calls it, but he calls it something else, and I just like L1 bar. I think it's the most natural name for it. Now, Mustafa's paper, I think, is definitely the best paper around for this scheme, in the sense it's the only one that produces an n-squared error analysis. It's a good paper, but it leaves some things undone. It's not sharp as regards the degree of mesh grading, and the paper says this quite honestly. It points out that it says if you do a certain amount of mesh grading, then you can prove you get second order accuracy. But the numerical experiment showed that the theory in this paper asks for too much mesh grading, more than you really need to get second order accuracy. And that's bad, because too much mesh grading, especially if this can have this in order, you can get a lot of points then clustered near the initial point t = 0, and it may cause rounding error problems, or it may be inefficient connections. But the mesh points are not distributed in a good way. They are crowded too much towards t = 0. So this is a weakness of the paper, and this is something that we believe we can improve. We can get something sharp as regards the amount of grading. So let's talk about how we discretize the differential equation. This is the differential equation here, the Kapitha derivative and some split this elliptic spatial operator. We begin by averaging over each time interval. So we integrate each time over interval and divide by the length of the interval. This is, you might say, the obvious thing to do because of the method we're using, which fits naturally with this bit here. Different notation for any function b, this notation, and it means simply the ordinary average, nothing complicated, of the function of the value. That's the time tn minus 1, and the function of the time tn divided by 2, that's all. In our numerical method then, if I write large U for the computed solution at each point, we have some kind of mesh here. It isn't special. I have a special mesh in time, but in space, I'm going to assume I don't have any problems. I'll just use some ordinary mesh. So at each mesh point in space, you do something like this. First of all, you replace this first term by the L1 average discretization, the scheme I talked about on the previous slide. In space, you do some kind of discretization. For the moment, I'm not going to say what. It won't affect a lot of the analysis. At the end of the talk, I'll talk a little bit about finite difference, finite elements. But the talk is really about what to do with this graph. And this is just average, just take the discretization in space. You take the value at Tn, you take the value at Tn and you take the average in this sense, just like so. And similarly with the right-hand side G, you just take the average of Tn and Tn minus 1. We have some initial condition, which is some projection of the original initial condition, and we have the boundary condition here, which is just 0. Okay, so that's the discretization. In a sense, this and the next section of the main part of the talk, first of all, these two sections are all about discretization and time, so space doesn't really impact. So I work with functions that are functions of t only, just notation. So suppose we have a function v of time on the interval 0 and 10, and it satisfies these bounds. These are the same bounds I had back at the start of the lecture on putting the pseudo solution, except there's no sublet known in space. These are just pointers. Some positive constants m and sigma. Okay, let's look at the definition of the truncation error of our method. So we took an average of the Caputo derivative over time, over the time interval, and we approximated by our L1 bar scheme. And you remember the L1 bar scheme is got by replacing v by the piecewise linear increment of v, that's pi of v. So this is the same as this, and so we write it like this. And now remember the definition of the Caputo derivative. It says you take a derivative in time, and then you apply a linear operator. So this is just the definition of that guy. And then the last line is just write out the definition of this I at 1 minus alpha. Exactly this. So you take the derivative of this function, you multiply it by this omega 1 minus alpha, which I remind you is some constant which doesn't matter, multiplied by t minus s to the minus alpha. You multiply it by this derivative of this function, and then you integrate the time. So this is exactly equal to that. It's just the definition of what's here. And theta v, again, for convenience and notation, this is the error in the piecewise linear interpolate of our function v. So our truncation error for any function v looks like this. And the challenge is to get a good estimate of this is using what we are allowed to assume. Okay, here's the same formula again that we just said. So first of all, do a little bit of rearranging. Now, go from this line to this takes about 4 or 5 lines of calculation, but it's elementary stuff. You swap the order of integration, you do some rearranging, you do an integration of parts, and you can do this. It's just some calculation, it's not hard. Now, let's talk about this. Remember, this is truncation error. Our target, what we're trying to do is to estimate this and get it as small as possible. So here we have an integral from 0 to tn of theta v multiplied by a weight function, and the weight function is basically tn minus s to the power of minus alpha. It blows up when s goes to tn. Here is something very similar. Theta v again, the same function, multiplied by this guy, which blows up at the upper limit of this interval. This is tn minus 1 minus s to the power of minus alpha. So this near tn minus 1 is like this, near tn. Of course, theta v is a bit different. Here s is near tn, here s is near tn minus 1. Also, the length of this integral of interval of integration 0 to tn minus 1 is not quite the same as the length of this. But there are some similarities in the way the two kind of blow up, and that's why we rearrange this into this form. I'll go a bit further. Okay, I need to estimate this. I'm going to do, for n equals 1, 2, and 3, you estimate this directly. What I mean is, you write out in detail what the terms are, and you just do some estimating. You have to compare terms. It's kind of ugly if you just do some small estimates. But the real interesting case is when n is bigger than 3, and then you do a certain integration of 4, you break this en, this truncation into 3 pieces. n0 is the integer, the smallest integer bigger than n over 3. Don't worry about this smallest integer bigger than. Think of n0 as n over 3. Think of n as n. And when n is 1, 2, 3, this isn't quite right, so that's why I do this as a special case. But for integration of 4, that's the interesting case. So for the when k goes from 1 to n0, so k is the biggest k can be is n over 2. So on these integrals, we are not near n. k is as big as n over 2. This guy, s is not near tn, it doesn't blow up. And similarly, this is not near tn minus 1, it doesn't blow up. You can just subtract these directly and you can estimate this. Then there's a single term we leave on its own, which is this guy. This is the fact that this integral is a little bit longer than this integral here for integrating. And we need to subtract out one term in the middle, and we do it. And we get these the same length. And we do this, so we do this little guy all by itself. And then finally, this is what's left. And these again, these are the same, this is more or less the same length of integral, with the interval over which you integrate. They're not exactly the same because the length isn't uniform in general, but they're close enough that it will work. That this and this have a lot of similarity, and you can subtract terms and do some calculations. And then I'll just say each of these is bounded separately, each of these three terms. It takes a while. This is far from trivial as well. Do it. But I think this is in some sense the key idea, that you break it up in exactly this way, and then you can cope with each of these in some sense in a natural way. You don't have any strange constructions, strange estimates, but it takes time. You get. So this is the third and final slide of this truncation error. So let me define the function. I won't really talk about this except to say that under our hypothesis on the truncation error in absolute value is bounded by this field right here. This is what we get. And the proof of the theorem, the proof of this result, I indicated from the previous slide basically how you break things up. It's pretty long. It's 5 pages of analysis. It's at least the way we do it, that's the best we can do. It's we had a longer version originally. Five is an improvement, okay? But I'm basically saying it took us a lot of work. Maybe someone else can do something better, of course, I don't know, but this is the best that we can do. But we come to this estimate. Now this is, I'm not really going to talk about this, it looks complicated, but it turns out it's enough to deliver this is a truncation error estimate, not a final convergence estimate. We need some stability argument to get from here to convergence, and it turns out this is enough to give us finally a good convergence result. But the truncation error analysis needs 5 pages, but this took us a lot of work, and let's not just leave it at that. Right. Now, the truncation error analysis is, that's truncation error. To go from this to convergence, I need some sort of stability analysis, and that's this section, and it involves the sign pattern of the discretization. So the definition of this discretization here it is again. Now here I'm going to skip a lot of details, but you can write it as a sum like this, or you can write it like this. These numbers kappa, check the definition back here, you can easily verify that this is true. It's not instantly obvious, but if you write out the details, then the k to n k, you just rearrange this and you can figure out this. So this follows me. And we would like these guys to have a certain sign pattern, because if so, if they do have a right to correct sign pattern, we can do a certain type of analysis. Now, let's talk about the sign pattern. This is just reminding you the notation Tn is the mesh, and tau n is the mesh width. The length of the nth interval. So I'm going to define rho n to be the length of the n minus first interval divided by the nth interval. Now it's easy enough to see, maybe you can see it instantly or a short calculation, that as n increases, the tau n's increase as well. The mesh is fine at t equals 0, and you come away from t equals 0, it becomes gradually less fine. So this rho n is always less than or equal to 1. It's positive, of course. It's equal to 1 if you have a uniform mesh. It's less than 1 if you have non-uniform. In other words, the tau is uniform. So this is a trivial observation. Let me just write down this function of the over just two events. We have a lemma. Assume that alpha is bigger than this value, which is about 0.43. Okay? Then C of alpha is less than or equal to 1. So this first statement, this 0.43 or 0.45, just looking at this function and asking the question, alpha is between 0 and 1, put x equals alpha. For what values of alpha is this less than or equal to 1? Why I need this will become clear in a moment, why I need it less than 1. And the answer turns out with a little bit of calculation and analysis, it's elementary, of course, that the psi of alpha is less than or equal to 1, provided alpha is bigger than or equal to this value. Now, from here on in the talk, I'm going to use this inequality to make things work. So I will not have any theory when alpha is smaller than this. I only have theory when alpha is between this value and 1. Let n be the mean value. Suppose we have this inequality. Now, this is difficult to understand what it's saying, so I'll talk more about it on the next slide. Just believe me for the moment. If you have this inequality, now rho n is the number here, it's less than or equal to 1. So the only way this inequality could possibly be true, it might be true, it might not, depending on our mesh grading, depending on alpha. If the only way this can be true, because the left-hand side is at most 1, it can only be true if psi of alpha is less than or equal to 1. And that's the reason I'm interested in this inequality. If psi of alpha is bigger than 1, then this cannot possibly be true. So that's why I first of all consider this, and I say, okay, we have to live with alpha being bigger than 0.43. We can't get anything else. Then if this inequality is true, then we can write down these patters that were on the previous slide. These guys here, we can calculate them exactly, and we can prove these inequalities. It turns out the first inequality is the only problem. The rest of these inequalities are all true for any alpha between 0 and 1. It's quite easy to show that. The first one is troublesome, and to get this, you have to do some analysis, and it turns out that this inequality will be what you want. So provided we have this inequality, then we have all of these. So let me just check the time, please. Okay. And so provided I have this inequality, then we have all of these. Now, later we'll see why this is helpful. On the next slide, I want to talk about this. What is it telling us? It says something, okay, we know what rho n is, psi alpha is written down in front of us here, and alpha is given to us in the problem, so we can calculate psi of alpha. But it's not clear in terms of the mesh. The mesh is defined in terms of R, the mesh gradient. So I would prefer to have a new inequality in terms of R instead of in terms of rho n. That's what we do next. So n can be any value. Suppose R is less than or equal to this value, and then it turns out using the previous lemma you get the same inequalities together. Okay? So this is just a way of saying if I have this condition on R, if R is not too big, then I will get the sort of inequality that I want. And remember, R is the mesh grading. It's always greater than or equal to 1. So I can only use this inequality if the right-hand side is bigger than 1. And if you again calculated this, do a little bit of elementary numerical analysis, I suppose, or get a calculator, you will find that the right-hand side is bigger than 1 only when alpha is bigger than this. Now, we had a condition on alpha a minute ago on the previous lemma, which is slightly smaller, alpha bigger than or equal to 0.4 or something. Okay? So this is even more restrictive, but I can't avoid it. The previous lemma, in some sense, is more precise. It says that if you have this, then you get this. The second lemma is in terms of R, and it's not. It's derived from this, but we can't derive it in a totally sharp way. We get the same conclusion. The condition on R is this, and the only way I can possibly use this is if the right-hand side is bigger than 1, because R is automatically bigger than or equal to 1. So it's only if alpha is bigger than or equal to this value that this inequality makes any sense. If alpha is smaller than this value, the right-hand side is smaller than 1, and this inequality is never true, so the lemma is useless for me. So I can use the lemma only in this situation. Well, this is the last lemma of this slide. From here on, we will have this condition, but it doesn't get any worse. This is the foundation condition. Now, let's first of all talk about the initial value problem. I will come back to the initial boundary value problem, but it turns out that if you can analyze the initial value problem, then there's a certain way of getting it fairly quickly towards a big problem, the initial boundary value problem. So let's take a pure initial value problem with the same Caputo derivative, t in 0, 2. There's some initial condition, and the L1 bar discretization, which would be like this. So this is the kind of thing we did in our initial boundary value problem. on our grid, so the same mesh. So all I've done is I've thrown away the spatial component, spatial derivatives and so on. I've just reduced it to a pure initial value problem. Okay, assume the solution like this. Now this is basically the same hypothesis we had earlier in here, but using a different form. Less than or equals like this. Shouldn't define this formally. It just means less than or equal to some fixed constant. I'm sorry for this big indentation. Assuming now that the mesh grading parameter R, this is the same condition that we just had here. So assume that the mesh grading parameter R satisfies this. Then the scheme has a certain sign property, and we can go ahead, and I'm not telling you what I'll give a reference in a moment. There's a certain type of analysis you can then do. Well, there's a paper by Natalia Kopteva, Math 2019, very strong, very useful paper, and essentially that's what we use to get this conclusion, that it has a way there of proving stability, provided that it meets a certain sign property. When we have our less than equal to this, then our scheme does have the correct sign property to use this paper, and then we can prove this. This is what we get. For our pure initial value problem, the error between the true solution and the computed solution, the maximum error over all the mesh points, is bounded by less than or equal to some constant times n. Remember, n is the total number of sigma is this guy right here. And certainly for a pure initial value problem, usually sigma would be alpha. In fact, think of sigma equals alpha. So you get n to this power here. So I said at the start of the talk when we met R, that R is the mesh grading. It's bigger than or equal to 1. We can choose it, but how we choose it, we don't know yet. The theory will tell us. And this is the moment when the theory tells us what to do. Numerically, the best you can hope through this scheme is second order convergence. And this says to you that to get second order convergence, you should take all bigger than or equal to 2 divided by sigma, so that this minimum is equal to 2, and then you will get into the minus 2 second order. So this tells you that how much but there is maybe a problem. As I said, it's clear from here, you should take all bigger than or equal to 2 over sigma, or bigger than or equal to something. But here we have a constraint or less than or equal to something. So, can you pick R the way you'd like to here? Now that the theorem, this conclusion is true for any R, provided it satisfies this inequality. So R could be equal to 1, for example, and that would work. Okay? But in order to get the best possible order of convergence, I want R bigger than 2 over sigma. Whereas here, I'm just losing this inequality. Can I do both of these at the same time? So that's the question. To get second order convergence, you should do this. To get R less than equal to this, we have the upper bound. Can you do both? Okay? In fact, I now realize I told you something wrong earlier. That was the last condition on alpha. Sorry, here's the last condition on alpha. Let's take the case sigma equals alpha, which is the most natural case to analyze. And you ask the question, for what sigma equals alpha? For what values of alpha is it the case that you can satisfy both these inequalities together and it's just elementary analysis? The answer is this. If alpha is between this number and 1, well, approximately this number and 1, then you can satisfy both these things simultaneously. In other words, our theory works. If alpha is between here and here, then you can choose R like this, and you can choose R equals 2 over alpha, and it will satisfy this, and you will get second order convergence. Now I will go on to talk about the initial value problem, the initial boundary value problem in a moment, but it will be the same condition in R. The same condition in alpha. And provided alpha is in this range, you can choose R to be 2 over alpha, and you get second order convergence. It will be the same thing, but the fact you have the spatial derivatives may cause any difference. But this is good up to a point, but it's not perfect. Sigma equals alpha. It turns out, our theory says that when sigma equals alpha, this choice is second order convergence provided alpha is in this range here. but in fact, numerically, you will get second order convergence for all alpha. So our theory in that way is not sharp. It just says that we can only prove the result for this value of alpha, but it turns out numerically the same result is true for all alpha 0, 1, and even. Our whole approach, there's no way we can fix it or extend this. This is a weakness of our analysis, but there's something good about it that I think something strong about it. So let me come back to the finally the initial boundary problem. Okay, this slide is just a reminder. We're almost done. I'm not going to spend too much time on this spatial problem because it's actually straightforward using Cocktail's theory. So this is the original initial boundary value problem. We saw this at the start. This is our discretization. We saw this before. And as I said before, AH is some discretization of A. And on the next two slides, I'll talk about, first of all, finite difference, and then secondly, finite element discretization. Okay. Now, if you look at Natalia paper, MathConf 2019, it's very general. There's a way of doing the stability, which we've used already in our paper, and then you can combine it with more or less any reasonable finite difference or finite element discretization, AH or AOI. Here I'm being a bit careless. Any reasonable finite difference, simple finite difference, and maybe there's some restrictions on the finite element discretization. But basically, our analysis is very, very general, provided you have the right correct sign and the time discretization. So here's the finite difference result. I didn't give here a full detail, I want to fit everything on one slide. Suppose you have something like a second order derivative in space. You do a standard 3-point scheme to discretize it. Nothing special in space. It's only in time you do something special. And similarly, if you have a UYY, you do a 3-point discretization in the Y direction. This is on a uniform mesh, assuming a domain like this. Okay. So as I say, in space, nothing special. You need a simple finite difference discretization, which has a nice sign pattern. Assume that C is greater than or equal to 0, so we can use a discrete maximum principle. Assume the kind of bounds like this that I've changed my sigma to an alpha here. So assume that basically this says in space there's no trouble. The derivatives, at least the derivatives that we need, are bounded in space. And assume that we have the earlier mesh grading in our lemmas, so we need this. There's a condition on H, like you get in every numerical analysis paper. H has to be sufficiently small, the mesh in space, but this is a very mild condition. It just says H is less than or equal to some constant. It's not a problem to have in practice. And then the discretization of the initial boundary value problem has a unique solution, and you have a pointwise estimate. This is finite differences. You have the same estimate as we saw already for the pure initial value problem, and you have second order in space because it's that kind of discretization, and the solution is well-behaved in space. So you get this is not a surprising after you see the Now, in order to get this result, I have this restriction on alpha. Provided alpha satisfies this inequality, you can pick R to be any value you like. Okay, if you want to get second order convergence, then you have to restrict alpha a bit more in order to keep R big enough to get 2 here, and you need this alpha greater than or equal to 0.6 something that was on an earlier slide. But that's only to get second order convergence. I repeat, this inequality is true provided alpha satisfies this, and you can pick R. So in other words, the spatial discretization, it adds some theoretical complication, but it gives you a result that's and then finally, the finite element discretization. Here we can go a little bit more general. Finite element space of piecewise polynomials between L greater than some quasi-uniform triangulation of the spatial domain. Make assumptions like this now with them. Sorry, I guess this is okay right now. Anyway, I'll just go ahead because the time is up. You need some assumptions which are more stringent now if L is larger on the solution. Some more stringent in terms of the spatial derivatives. And then we have assume this. So this is the kind of typical condition you have for finite element analysis, C minus a half div B greater than or equal to 0. Assume again this condition on alpha, and then you get a bound in the L2 norm like this. And again, it's like we saw with finite differences, the same bound in time and a finite difference, finite element type bound in space for the L2 norm. In the particular case, L equals 1 with some extra hypothesis on the triangulation of all acute angles, something like this, you can actually get an infinity bound at any individual time level. You can get a bound like this. Again, just by copying using finally, are these results sharp? Well, this is what we want. Numerical results, let me take sigma equals alpha to keep this simple. We have a bound like this. Now I wrote it only for the time derivative, the spatial derivative for some power of h, but the time bound is really the crucial part. We have a bound like this, provided r satisfies this. And this in fact is sharp dependent on r, provided r satisfies this. If you vary r, you get exactly this power of h. If r alpha is bigger than or equal to 2, you get second order. If r alpha is smaller than 2, you get h to the minus r alpha. So in terms of dependence on r, it's quite sharp, unlike Mustafa's paper, which is not sharp dependence on r. That's the good news. And the bad news is something I told you already, that if we want to get second order convergence, we need r greater than equal to 2 alpha, but our theory, because of various inequalities, we can only push our theory through, provided alpha is bigger than or equal to this. Actually, I'm sorry, that's a misprint. It should be 0.6 something, not 0.529. I'm sorry, I copied the wrong number. But it's a number 0.6 something. It's not too restrictive. We still have a good range between 0.6 something and 1. But the numerical results show you don't need this at all. For all alpha, you get this. So our results are sharp in terms of the dependence on r, but they're not sharp in the sense of when you can prove that we get second order convergence. We have a restriction on alpha that's not actually needed in practice. So as I said, I think it's definitely better than Mustafa's paper, if I may say so, because of the sharp dependence on r. But the job is not complete. There's still something to be done, but I don't, as I said earlier, I don't see any way of improving this part in our techniques. And that's the end. There's a preprint you can find on research page, or the exact address of the preprint, and put it through this today. And thank you very much for your attention.
Okay, thank you very much.
Sorry, I didn't understand the end of the question. It's a good property in the case of what mesh?
Yes, my question is the average the L1 method can benefit of this better convergence property also with equispaced method, equispaced meshes, or just with graded meshes?
We only look at graded meshes, and both theoretically and numerically. So I don't know if you have some different mesh in time. In space, we just assume everything is nice. We really did no experiments in space or having significant. And in time, we only looked at graded meshes, but we didn't try anything else. I guess my own belief is that these kind of graded meshes that we use really work very well. And I feel lazy. I don't want to try any other mesh. I think this is as good as it gets. I know some people have proposed other meshes, somewhat different. They all cluster points near t equals 0, of course. But I think this graded mesh, which is old, it's around 20 at least years, I think this creative mesh works really well, and I feel no desire to try any other mesh in space. Maybe I should, but I'm going to stay with this. So I don't, to come back to your question, I'm sorry, I just don't know. I only know for the creative mesh was what happened.
Usually this is the final of the championship yesterday. The coffee break will change it in a champagne break. So we will see, we will meet together in a few minutes. Okay. Thank you.
che abbiamo la slide, questa qui, e poi anche 16 noni sta slide. Vuoi andarti a drogare?
Prendere del caffè perché sennò vado ci rendi pronto.
Anche io, e quindi ora ci andiamo a drogare insieme, molto volentieri. Io farei leggermente un crop, ma proprio piccolo piccolo. Non lo so.
Scusa, anche se dici se lo fai un formato strano. Perché questo ti mantiene l'aspect ratio, no?
Sì. E lo butto un pochino più qua, va bene, così perfetto. Adesso
So welcome back after this champagne break here in Rome. Okay, so I am happy to introduce now Roberto Garraffa from University of Bari. He will talk about variable order fractional calculus, a change of perspective.
Thank you very much. Well, just a moment. Quando va in formato presentazione non va più. Okay, in this talk, we'll present a different approach for defining variable order fractional operators. So I will first provide the motivations for this work. I will describe the theory, and in particular, I will talk about some numerical aspects. This talk comes from a joint work with Andrea Giusti from the ETH in Zurich and with Francesco Menardi from the University of Bologna. Here is a list of institutions which supported this research. Well, just to talk about the motivation, we know that fractional calculus is used in general to describe processes with the memory, such as in sedimentology for describing the flow of fluids in porous rocks, or to describe special materials with anomalous properties. For instance, toothpaste, but we can think for more serious applications such as asphalts or polymers, biopolymers, and other special materials. Why we use fractional calculus? Because fractional calculus is able to describe these memory properties of these anomalous properties of the materials. But in lots of situations, it is necessary to take into account that these anomalous properties may change with respect to time or with respect to space. For instance, when we try to describe the dynamics of volcanic lava, we have to consider that volcanic lava acts as a viscoelastic material, but their properties change as the lava cools. Or if we describe concrete or asphalt, as the materials dry, their properties change. So it is necessary to introduce some memory effect which change in its main characteristic with time, or maybe with space, as for instance in some application that will be described later on and taught by Andrea Giusti on attraction, Newtonian gravity, and galactic dynamics. Well, in the past there have been several attempts to introduce variable order fractional derivative. Maybe the more direct approach is to replace the constant order alpha with a function depending on time. But an approach of this kind has some drawbacks, because we know that especially for numerical treatment, in most cases we necessitate of an integral which inverts this operator. And if we build an integral with the same replacement of the constant order alpha by a function, we have that not for any function, we have actually that the integral is the inverse of the derivative. And this usually creates some problems, both from a numerical point of view, but usually also from the theoretical point of view. This is a very old result. I have to say that our approach is not completely new, because it relies on some very old idea by Giambattista Scarpi, who is an engineer, mechanical engineer in Bologna, who had some preliminary ideas in 1972. So I think it is almost 50 years ago. And this approach is based on the Laplace transform. For a long time, this approach has been substantially neglected. And but nowadays it's possible to frame the early ideas by Scarpi in a more general theory of fractional derivatives and integrals, a theory developed by Kuchbey and more recently by Yuri Luchko. And in particular, we are now able to couple this theory with robust numerical methods. As we will see, we will not have an analytical representation of the operators, but these operators are known in a quite abstract way, and we will need an intensive use of numerical methods for the treatment. Well, let's now describe these new operators. We start from the classical definition of the Caputo derivative, which we know, which can be written as a convolution integral of this function phi, which is this power of alpha, and then the first derivative of f. We see that the Laplace transform of the kernel is s power to alpha minus 1. Well, in order to replace in this definition the constant order alpha with a function, we consider a function of which we know is the exact representation, is an analytical representation of its Laplace transform. Well, let's come back to the constant order case. So when alpha t is equal to just a constant alpha, we know that its Laplace transform, A of S, is actually alpha of S. So the kernel of the Caputo derivative, which is phi of S equal S to alpha minus 1, can be written, if we consider the constant case, as this power, where clearly now, with the constant case, capital A is the one which is written here. But we can generalize this approach to any variable order function of which we know exactly the analytical representation of the Laplace transform. And then we can create a kernel, better, the Laplace transform of the kernel here exactly in the same way as we have shown before. But now, capital A is not just alpha over S, but is actually the Laplace transform of this transition, we call it a transition function, which is the function which describes the transition of the order from one order to the other. And so we define in a very similar way as the Caputo derivative, the new derivative. We indicate this derivative with this symbol S, just to recall the early ideas by Scarpi. In this way, as the convolution integral, where now the kernel is not known, but is the inverse Laplace transform of the kernel, which we have created by means of the Laplace transform of